So, hello, welcome to the second lecture in the online course on analysis and modeling of welding. This lesson is titled heat sources. So, the heat sources that we are going to discuss will be applicable for both joining and cladding. In the case of joining, we are seeing in the schematic two base materials are being joined, and then you can see the arc or beam, which is the heat source, that is giving the heat to the joint between the two pieces, and then as the heat source moves or the base material moves in the opposite direction, we have a bead that is made, and we have labeled it as weld in the schematic. And in the case of cladding or weld overlay, a very similar process is taking place, except for that there are no two different pieces that are being joined, but only a material is being deposited as a track on surface of a base material. So, we do have again the arc or the beam that is giving the heat source, and then in the base material the heat is actually falling on a location, and then as the beam moves forward or the base material is moving backwards, we have the melting of the powder or the filler material, which can be given in the form of a wire, for example, and then a deposit is made as a track, and then these tracks can be overlain on the base material side by side, so that we can make an entire layer coverage on the surface of the workpiece. So, both the joining and cladding processes use heat sources, and we are now going to go in depth on how these heat sources can be modeled and analyzed. So, very often when we read a journal article which looks at the analysis of joining and welding, we look at boundary conditions which they have used to understand how the heat transfer has been modeled. So, usually we have the heat source boundary condition, the heat loss boundary conditions, and we normally encounter a Gaussian heat flux as an input condition for heat on the surface, and then we have convective losses being taken care by use of a heat transfer coefficient H, and then the radiative losses are also taken care. Some of these may be extended with the different terms on different sides of the material that is being joined or clad. So, it is important for us to ensure that these conditions are understood very well before we apply to a situation in industry, and therefore, we are going to go in depth one after other. So, in this particular lesson, we are going to look at the first aspect, namely the heat flux, to show that Gaussian is, while being most popular, is also not adequate for many of the situations that we encounter in real life industrial scenario. So, the physical processes that take place during welding I have listed here, they are like heat transfer, fluid flow, mass transfer, and so on. And then during welding, the material usually undergoes phase transformations, and then there are also effects due to stress. So, it is very important for us to understand that all these processes are taking place simultaneously. However, it is difficult to solve a problem with taking all these processes simultaneously into account. So, what we normally do is to decouple these processes. In other words, we understand each of these, analyze, and then we will see how the information from one effect can be taken as an input to the other effect, and then sometimes the loop can be closed completely, and then we can proceed to have the solution of the particular welding problem we are looking at. So, in this particular lesson, we are going to look at the heat transfer alone, and while it is being affected by the rest of the things, we are not going to look at them at this point. So, the heat transfer, when we look at it, is a very extensively understood process. However, we are going to limit the scope for this lesson as follows. Heat transfer to a weld will be basically from a heat source from the welding source, and then we also have additional heat source sometimes with a leading heat source, that is in front of the welding torch we may have another torch which gives a preheating locally, which can be, for example, in tandem. We also have what is called a tandem welding, where you have two torches that are doing the process simultaneously, and we also have situations like hybrid welding, where there may be a, for example, arc welding and laser welding simultaneously being done on a sample, one torch behind the other beam, etc. So, you also have situations like external heat sinks to remove the heat, so that the thermal distortion can be controlled. So, you could actually look up the source and sink as just two aspects of a focused and localized heat transfer, either positive or negative in sign, and I have given in blue the 3 which we will be covering in this lesson as a one module under heat sources. The rest of the things that happen, for example, heat loss by convection mode, by radiation or by conduction to the base material, and extensive heat loss through the water cooled backup setup, etc. These are going to be looked at in the thermal modeling lesson later on. And we also have situation where there will be heat released in the weld pool because of exothermic reactions that could take place when there is a powder that is being fed into the liquid melt, so that it can form some special layers on surface. So, such situations are also not considered in this lesson. And during heating, what normally happens is we have the heating of the base material, and then eventually the melting point will be reached, and then we have the melting of the material forming the liquid melt pool. And then sometimes the temperatures could be reaching high enough that locally evaporation also can take place. And then eventually when the torch moves ahead, then the liquid melt will solidify to form the solid material behind the torch, and then eventually that gets cooled to the ambient temperature. So, this is a cycle where the heat is given so that the material is heated up and then is cooled back to the ambient temperature, and these are dependent on the heat source very crucially, and therefore, understanding the heat source in depth is important. So, the heat sources in welding processes, we have already seen a list of welding processes in the previous lesson, and we are only going to take out the heat source alone for the purpose of this lesson, and there are a lot of heat sources that we are going to look at. The most important heat source would be arc, electric arc, and then we also have a plasma as a heat source, and electrons are heat source, for example, in the case of electron beam welding. And then lasers, different types of lasers are there which act as a heat source, and we have generally observed in industrial environments such as Nd:YAG laser, carbon dioxide laser, excimer laser, etc. And when we have sometimes also infrared sources as heat sources. We have not looked at infrared source as a welding source. However, we do have the possibility for surface treatment and surface coatings which form as an allied process for welding. So, infrared sources also form one of the heat sources that we are looking at, and sometimes we have the filler which is being added. So, it can generate heat by exothermic reactions. It can also consume heat because it needs to heat up and melt and then mix with the liquid melt pool. So, you could also choose to have the filler wire or filler powder as a heat source or sink, but in our lesson we are not going to look at that. So, we are going to look at the top 5 items that I have listed here. So, what are the various characteristics of heat source that we need to analyze it? So, here I have listed some of those characteristics. So, the nature of distribution, that is the spatially how is the heat distributed on the surface of the base material is important, and most of the times the heat source will be taken as a surface heat source. In other words, it is only acting as a boundary condition on the surface of the base material that is being joined or molten locally. Sometimes, as the situation may warrant, in the case of say keyhole welding, you do have what is called as a volumetric heat source also possible. So, it is important to know whether the heat source that we are looking at is a surface heat source or a volumetric heat source. And then the power distribution in terms of the spatial variation should be available to us. In other words, it should be a function of either xy or xyz, as the case may be for surface or volumetric heat source. And it is also sometimes possible that the variation may be with respect to the material also. So, there are situations where the absorption of the heat source on the material depends on the material, the temperature of the material, etc. So, you may actually have power distribution that may come as a function of many other parameters apart from just being spatially varying. Sometimes it is also possible that the heat source is changing in time. In other words, we may have pulsing effects. The lasers, for example, are very popular in that sense. You do have a pulsed laser to be used for welding and surfacing or surface treatment. So, where the heat is given in a short pulse and a number of such pulses are given one after other to the material. So, it is important to know, for example, what is the pulse width, how much time the pulse is on, and then how much time the pulse is off between two pulses, and then how many pulses are we giving in a given amount of time per second, for example. So, like that we need to understand the temporal changes, that is the variation of the heat source as a function of time also to understand how the heat source will affect the thermal processes that take place during the welding. The traverse rate essentially refers to how fast is the heat source moving on the surface of the material that is being welded. So, it is nothing but the velocity of the heat source because the heating is happening just right under the heat source. So, you could actually look at it as a traverse rate of the heat source, and sometimes the heat source cannot be moved, and it may be the material that will be moved in the opposite direction. So, you may have a situation of the traverse rate being referred to as a heat source motion or the base material motion, as the case may be. And which way does it move? Does it move linearly or does it move in a zigzag manner is also something that is going to play a role. So, very often the path that is taken by a weld heat source is linear and it can be programmed by a single drive, but there are situations where you may have a rastering action for the heat source. By rastering, what we mean is moving back and forth to cover a wide area. This is often practiced in situations where a very wide pool is required, however, the heat source is focused, that cannot be extended to that much of a width. Oscillation also can be coming in reality. For example, magnetic arc oscillation is sometimes used to avoid central line cracking, and therefore, we may also want to look at the heat source whether it is moving in a oscillated manner across the path during the welding process. So, we need to observe all these quantities and then capture them in the model that we are choosing to represent the heat source. So, we often refer to the efficacy of how the heat source is able to deliver the heat to the material using a parameter called as heat source efficiency. Heat source efficiency is nothing but the ratio of two quantities. On the numerator, you have basically the amount of heat that is actually transferred to the base material, and the denominator is the amount of heat that is nominally provided by the welding process. So, very often the nominal heat is drawn from the socket in the case of electric arc, or it is a setting on the laser welding setup, etc. And the ratio is very often much less than 1 to indicate that the heat is not completely transferred, some of it is lost. So, we have a lot of ways to understand why the heat is lost. However, we have to appreciate the fact that heat source efficiency is very important because it is going to tell you how much of actual heat is transferred, and that is what is going to be used in the model. The nominal heat is only an indicative factor, but the product of nominal heat and the efficiency is what goes into the modeling efforts of understanding the welding. For the lasers, the absorption efficiency is going to be very tedious. The reasons are as follows. First of all, most of the lasers are very inefficient in transferring the heat to metallic materials. The reason being that metallic surfaces are like mirrors, they reflect light very easily. So, most of the time at room temperature, the kind of metallic materials we have in the industrial alloys that we use, like for example, copper based, aluminum based, etc., the surface absorptivity is less than 3%, which means that most of the heat is actually reflected back and is not being used for the welding purpose. So, obviously, we need to take into account that while choosing the process and also in modeling the same. And the absorptivity depends upon a number of quantities. It depends upon obviously the melt, the metallic material that is being molten and being joined. So, there are materials like copper which are acting like a mirror, so they do not absorb much of the laser light, and there are materials like for example, steel which absorb slightly better amount of laser light. The absorptivity is directly proportional to the frequency of the light that is being sent, or other words inversely proportional to the wavelength of the laser, which means that between NdAg which has a wavelength of about 1.06 micrometers and compared to for example, carbon dioxide which has a wavelength of 10.6 micrometer, you can see that the absorptivity with NdAg is better than with respect to the CO2 laser. So, wavelength of the laser is also very important. Shorter the wavelength, the better is the absorption on the metallic surface. The temperature of the material also plays a role in absorptivity. As you increase the temperature, you expect the laser light to be absorbed more, so that by the time we reach the melting point, the absorptivity will come to several percentages. And when the temperature rises to the extent that there is some amount of evaporation that has taken place, and then there is a vapor column, then the absorption reaches nearly 100%, which means that the vapor state of a material absorbs all of the laser heat, whereas the liquid absorbs only a few percent and the solid will absorb less than 2%. The phase, that is the liquid state or vapor state or the solid phase, is to be known when we are applying the absorptivity of the laser. In other words, laser absorption parameter is going to be a function of either time or temperature as we choose to model it. The surface condition of the material also plays a role in the absorption of laser. So, in the case of solid materials, the presence of oxides on surface will enhance the absorption, and the surface coatings also can be given so that we can enhance the absorption. So, very often a thin black coating of graphite layer is put on surface of metallic materials, so that it can enhance the absorption. Surface structure also can improve the absorption, and surface structures can be induced again by lasers or any other manufacturing process, and the surface roughness, for example, allows for reflection of light locally, and then provides more opportunity for the laser light to get absorbed on the surface. So, the solid materials, while they are being heated, the surface roughness and the surface structure do play a role. However, these are all only when the material in the solid state, and as the temperature increases to the liquid state, then most of these are gone, and then we now see how it is dependent on the temperature. And there is a whole book on only one topic, that is the laser absorption efficiency, and you could if you like read it in the book titled Laser Heating of Metals by Prokhorov, and the book is published by Adam Hilger, and I would advise you to look at it if you want to know more about how the laser light is absorbed by metallic materials. And even in general, I would advise you to pay attention to the literature from Russian side, because they seem to have done a lot of work in welding area. So, here is a summary of the heat source efficiencies including laser and arc, and these are actually organized from lowest to the highest efficiency values that we have found in the literature, and these are available with a lot of discussion in the book by Sindokov, and I am presenting here a summary. So, laser beam welding, as we have just now seen, has a efficiency much less than 10%, and that is the reason is because of high reflectivity of the metallic materials. And then comes the plasma arc welding, which has a absorptivity between 0.5 and 0.7, and the reason why plasma arc welding has slightly on the lower side of the efficiency is because there is a water cooled constriction nozzle that is surrounding the plasma jet, which is present in the plasma torch. So, because some of the heat is lost to this water cooling jet jacket that is surrounding the plasma torch, then we have some loss of heat, and therefore, the efficiency is slightly on the lower side. And then when it comes to rest of the arc welding facilities, normally you do have a good value between 0.6 and 0.9 going from GTAW in the electronegative mode to shielded metal arc welding and gas metal arc welding. The reason why in the electronegative mode we do have a higher efficiency is for both the two reasons, which is the kinetic energy of the electrons being absorbed by the material. The electrons that are accelerated towards the base material are stopped suddenly, and all the kinetic energy is then left to the base material, which then takes it and converts into heat, and that is one reason. Another reason also is the work function. As we know, when we want to remove an electron from a metallic material, then we need to provide some amount of energy, that is called as work function, and the reverse happens whenever electron is then given to a metallic material. The work function will then be released, and that will be also one part of the energy that will be released. So, in other words, when the electrode is negative, the electrons are going towards the base material, and then that gives a lot of heat to the base material, and therefore, the efficiency of GTAW process is on the higher side. And we do have also GMAW showing you very good efficiencies, and normally GMAWs are with electrode positive polarity, and the reason why efficiency is considered high is because the electrode actually melts, and those molten droplets of liquid at high temperature are again reaching the base material and giving the heat. So, in other words, the heat that is given to the base material and also to the electrode are both reaching the base material eventually, and therefore, the efficiency of GMAW is very high, reaching up to 0.9. Submerged arc welding also has a lot of efficiency, the reason being that the arc heat is not lost to the environment by radiation, because the arc is covered by granular flux which hides the arc and therefore, prevents some amount of radiative loss. And electron beam welding is known to show efficiencies reaching nearly 95%, and the reason is as follows. The keyhole mode of welding that is normally taking place during electron beam welding has a vapor column, and the vapor column acts like a black body to absorb all the energy that is given by the beam, and therefore, the entire heat will be dumped into the material, and in that sense the efficiency of electron beam welding comes to be the highest in all the welding processes. How does the heat source appear and how do we then model it? So, this is the extensive discussion that we are going to have now, and we can actually see the shape of an arc with naked eyes. It is not recommended because there is a lot of ultraviolet rays that are also coming. So, you could actually see the arc with your eyes by placing a filter and looking through it, and then you can see with your eyes that the shape of the arc looks like a decreasing nature with the maximum value under the electrode and going towards 0 away from the electrode, and the width of the arc is generally slightly more than the electrode, maybe up to about 2 times the diameter of the electrode. So, it is also possible for the electrode to be either sharpened to be a tip, or like a conically tapered, or just blunt. And what kind of an electrode tip shape would give you what kind of a heat source distribution is evident from this schematic image that I have shown. It is seen from here that if you have a blunt tip, then the diameter of the arc is decreased, and which also means that the power density is actually increased. In other words, the entire arc is restricted to a smaller width and the intensity of the power is going up, which means that when we have electrodes, we must pay attention to the shape of the tip before we identify what would be the power density that would be applicable for that particular process. And then the aspect ratio of the weldment also is affected by the conical tip angle, and this has also been studied experimentally very extensively, and people have shown that the weld aspect ratio increases with the increasing conical tip angle, and it will be the highest at 180 degrees, which means that when the electrode is blunt, that is completely flat. And as you can see that we can actually mathematically represent the heat source that we have seen in the previous slide by using what is called as a Gaussian function. So, the function itself is shown to you here, showing you that it is exponentially written in a form that goes as e raised to the power of minus x square, where x is the length, and in 2D you have not just one length, but you have in the 2 directions. So, you use the radius as a parameter r. So, you have e raised to the power of minus r square as a general nature by which the intensity is decreasing as you go away from the center of the heat source, and we have those numbers like 3 that are given to ensure that the variation is as sharp as what is normally seen in the actual arc, and the distance variable r is written not just as a function of distance away from the origin of the heat source, which is at x naught and y naught, but also as a function of time. The reason being that the torch is moving, and as you can see from the expression written here, the radius is changing with the y distance as a function of time, which means that the torch is moving in the y direction. Okay, that is the meaning of the second expression we have given. X naught and y naught is the location of the heat source, which is at the center, and then the q value is nothing but the nominal heat source that is being given multiplied by the efficiency of the absorption of heat by the base material. So, eta Vi, where V is the voltage and I is the current, that would be the power that is given, and that power is then distributed in a Gaussian manner. So, the appearance of the Gaussian heat source is shown here. It goes down like a hill going from a high value at the center to 0 away from the center. I have made these plots using a set of MATLAB scripts. I will be showing you various such heat source distributions, and those MATLAB scripts will also be uploaded into the course site, and you could then plot them yourself and explore those nature of the heat source distributions. And if you are not familiar with MATLAB, then perhaps you may want to also join the online course on MATLAB offered by Dr. Niket Kaisare from our institute on the MOOC in the same semester as this course is going on. So, there is also one more aspect that we need to keep in mind. What happens normally is, apart from the Gaussian nature of the heat source that is coming from the arc, we also have a situation where the shielding gas that is used playing a role with respect to the heat source distribution. So, I have shown here a toroidal space from where the gas is coming through, and at the center of the space is where the weld pool is located. To keep the schematic simple, I have not shown you the welding torch, which will be actually at the center of the toroid that I have shown. So, basically in the annular region, the gas is coming out and then going on around the weld pool, so that it is protecting the weld pool from contamination. So, we must understand that the shielding gas that is being used to protect the weld pool also has thermal conductivity, which means that it also can remove the heat, and therefore, we have to also pay attention to what is the shielding gas that we are using. So, if it is going to be, for example, argon versus helium, then we know that the helium has higher thermal conductivity, which means that the heat loss is going to be more if helium is going to be used as a shielding gas, and that information should reflect in the heat source formulation by a change in the efficiency or a change in the nature of the distribution. And information such as what is the shielding gas, if it does not enter the heat source distribution at all, then that means that we are actually neglecting some of the realities of the actual welding. The flow rate of the gas also plays a role. The reason being that if the flow rate is high, then it is taking away through convective heat transfer quite a bit of heat from the arc, and that should also play a role. And usually the welding processes are such that the flow rate is not varied much, because the purpose of the gas is only to shield, and it will be kept constant for most of the welds. However, if there is a change in the flow rate, then we must know and then keep that information also handy to modify the heat source as the case may be. The geometrical construction for flow also plays a role. If there is no geometrical construction, that means if the gas is flowing freely and then expanding as it goes away from the weld pool, then its velocity also drops, and that means that the rate of heat loss from the weld pool to the environment will be at a particular way. And in case if it is constricted, then we would see that the velocities of the gas going through the nozzle will be higher, and that means that the heat loss will be slightly higher than the previous case we just mentioned. So, geometrical construction, is it there or not, is an information that we need to know. And how far is the gas nozzle from the workpiece, that also plays a role. The reason being that as the gas is expanding and mixing in the ambient air, then you see that its velocity also goes off, and then if the nozzle is very close to the base material, then it has a significant amount of momentum and the heat loss will be more, and if it is very far away from the base material, then it may not be taking away much of heat. So, we must also know what is the height of the nozzle from the workpiece. The angle of the nozzle also plays a role. It may induce asymmetry in the heat source distribution. So, if the welding torch along with the gas nozzle is kept perfectly 90 degrees to the workpiece, then there will be a symmetry that will be expected from the heat source distribution. But if it is at an angle, then you may not have that symmetry if the shielding gas is going to play a role in significantly altering the heat source. And there are situations where you may have a gas curtain separating the nozzle and anything else that is behind the nozzle. So, you may have a situation where you may want to remove the heat through liquid nitrogen jet behind the welding torch, and then if you do not want the nitrogen to mix with the weld pool, then you may want to have a gas curtain made of again argon in between. So, such gas curtains also remove heat and then play a role in the heat source distribution. So, we must also know whether gas curtains were used or not, and whether they have played a big role or it can be neglected. But we must be conscious of all these influences that shielding gases will have on the heat source distribution. So, with that we conclude the first part of the heat source description, and then we will move on to the second part. We will be going to further details on combining the heat sources and other formulations.